The morning sun broke over the Tunisian desert on March 14, 1943, casting long shadows across a scene that would reshape everything Allied forces understood about their enemy. Staff Sergeant Michael Patterson of the United States Army Ordnance Department stood before the massive silhouette of a Tiger tank, its 56-ton bulk sitting disabled in a wadi 3 kilometers south of Kasserine Pass. The machine looked invincible, its thick armor plates reflecting the early light like the scales of some prehistoric beast. Patterson had seen dozens of disabled vehicles in his 18 months overseas, but nothing compared to this mechanical leviathan, abandoned by its fleeing crew. The air held the cool bite of desert night, and the smell of oil and cordite lingered around the abandoned machine. Patterson and his team believed they were about to repair just another piece of captured equipment. They had no idea they were about to uncover a secret that would explain why the most fearsome tank in the European theater was simultaneously a masterpiece of engineering and a monument to industrial desperation. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What these American mechanics would discover in the coming weeks would transform their understanding of modern warfare itself, revealing that the true battle was not being fought on desert sands or European fields, but in the factories and foundries thousands of kilometers away, where industrial capacity mattered more than individual courage. Patterson had spent 18 years working in the automotive plants of Detroit before the conflict began, rising from floor worker to master technician. His hands bore the scars of 1,000 repairs, burns, and cuts that told the story of his expertise. He understood engines, transmissions, and metal like some men understood their own families, could diagnose problems from sound alone, could feel imperfections through his fingertips. But nothing in his experience had prepared him for the Tiger. The tank had been abandoned by its crew 2 days earlier, after a track failure left it immobilized during a retreat. Intelligence officers wanted it operational for testing. Patterson's job was to make that happen. Corporal James Mitchell, a 22-year-old farm boy from Iowa, who had spent his youth repairing tractors and maintaining agricultural equipment in his father's fields, whistled low as he walked around the vehicle for the first time. "This is bigger than my daddy's barn," Mitchell said, running his hand along the armor plate with something approaching reverence. The metal felt cold, despite the warming morning air, smooth in some places and rough in others where welds joined separate plates. He rapped his knuckles against the hull, and the sound came back solid, dense, intimidating, without the hollow ring of thinner armor. "Back home, we got a John Deere Model B that weighs maybe 2 tons soaking wet," Mitchell continued, shaking his head in disbelief at the scale of the machine before him. This thing could crush it without noticing. Patterson pulled out his assessment clipboard. The massive tank measured 6.3 meters long, 3.5 meters wide, and nearly 3 meters tall. Its main armament, an 88mm cannon, protruded from the turret like an accusatory finger. Intelligence reports indicated the frontal armor measured 100mm thick, with side armor of 80mm. American Sherman tanks, by comparison, carried maximum armor of 76mm. Private First Class David Chen, a metallurgy student from California before the conflict, approached with the cutting torches and equipment. "We're going to need to access the engine compartment," Chen said. "Track's definitely the primary issue, but we should inspect everything while we have it." The team spent the first day simply documenting everything. Patterson insisted on photographing every detail, every weld, every bolt. The Tiger represented a different philosophy of armored warfare than anything American factories produced. Where a Sherman tank could be manufactured in 10,000 man-hours, intelligence estimates suggested a Tiger required 300,000. Where American plants churned out thousands of tanks monthly, German production of Tigers never exceeded 125 per month at peak capacity. Lieutenant Colonel Robert Hayes arrived on the second day, driving up in a dusty jeep that left a plume of sand in its wake. Hayes commanded the Army's Technical Intelligence Unit in North Africa, a soft-spoken engineer from Massachusetts who had designed bridges and industrial structures in civilian life, his mind naturally inclined toward understanding stress, load, and structural integrity. He was 41 years old, grey already threading through his dark hair, and he carried himself with the quiet authority of a man who solved problems through analysis rather than volume. Hayes stood silently for several minutes, simply observing the tank from different angles, his eyes taking in proportions, noting weld patterns, examining track configuration. Patterson recognized the look, had seen it in master craftsmen back in Detroit, the way a true professional assessed a piece of work before touching it. Then Hayes spoke, his voice carrying the weight of strategic implication that came from understanding not just mechanics, but economics. "Gentlemen," he said, gesturing toward the Tiger with one hand while holding a leather-bound notebook in the other, "this machine represents approximately 300 tons of steel, hundreds of hours of skilled machining, thousands of precision components, and production resources equivalent to building 20 Sherman tanks. Every Tiger they build is a choice not to build 20 Shermans. Every hour their factories spend making one of these is 20 hours they could spend making tanks that are good enough. This is not just a weapon, it is an economic statement, and I suspect it is a statement of desperation. But this one's better," Mitchell observed, his youthful directness cutting through the analytical atmosphere. "Isn't it better than a Sherman?" Hayes smiled grimly, the expression of a teacher about to deliver an uncomfortable lesson. "Better is a complicated word in warfare, son. Yes, this Tiger can defeat a Sherman in single combat, at almost any range. But warfare is not single combat. It is logistics, production, replacement, maintenance, fuel consumption, crew training time, and 100 other factors that never appear in performance specifications. Let's see what makes it tick, and more importantly, let's see what it costs to make it tick." The real discoveries began on day 3, when Chen started examining the armor plating more closely with scientific precision. He had brought a portable hardness tester from the mobile laboratory unit, a small but sophisticated device that could measure the strength and durability of metal by pressing a diamond-tipped indenter into the surface and measuring the resulting depression. Standard procedure called for random testing of captured armor to understand enemy metallurgy, to build a database of material properties that could inform anti-armor weapon development. What Chen found made him test the same spot 3 times, 4 times, then 5, convinced his equipment was malfunctioning or that he was somehow misreading the results. The numbers made no metallurgical sense, defying everything he had learned in his university courses about proper steel hardening techniques. "Sergeant Patterson," Chen called out, his voice carrying an edge of confusion and excitement that made Patterson drop the wrench he was holding. "You need to see this right now." Patterson climbed up onto the hull where Chen was working, his boots finding purchase on the rough surface. The morning sun had begun heating the metal, and waves of warmth radiated upward. The young private pointed to his testing device, where numbers displayed in a pattern that violated basic principles of metallurgical manufacturing. "The hardness readings are all over the place," Chen explained, his finger tracing across the armor surface to indicate the test points. "This section here tests at Brunel 600, which is incredibly hard. Harder than most tool steels we use in precision manufacturing. But 3 centimeters away, less than the width of 2 fingers, it drops to 400. And look at this." He moved his finger again. "Here it jumps back to 550. The variation is extreme, way beyond anything I have ever seen in production metalwork." Chen moved his hand to indicate a broader area of the hull, his professional training clearly disturbed by what he was finding. "In a properly manufactured armor plate, you expect some variation, sure, maybe 50 points across the whole sheet, due to cooling gradients or edge effects. But this is showing 200-point swings across distances you could cover with your palm. It is like they were using different metal batches and just welding them together without any quality control, or the heat treatment process was completely inconsistent across the surface. Either way, it represents a catastrophic breakdown in manufacturing discipline." Then Chen pointed to a section of armor plate near a weld, gesturing for Patterson to look closer. Even without magnification, hairline cracks were visible, running like spider webs across the surface, branching and interconnecting in delicate patterns that caught the light. "Not impact damage," Chen continued, his voice dropping to the focused tone of a scientist confronting an unexpected phenomenon. "There is no deformation around these cracks, no indication of external force. I think these are stress fractures, metallurgical failures from the inside out. The metal is so hard it is becoming brittle, losing its toughness, its ability to absorb impact energy without fracturing. This is what happens when you overharden steel, when you push the carbon content too high or cool it too rapidly. Patterson leaned closer, his trained eye recognizing patterns from years of quality control work in manufacturing. In his years at the automotive plants, he had seen similar patterns in poorly tempered steel, usually the result of rushed heat treatment or inadequate temperature control during hardening. The metal was hard enough to resist penetration, theoretically able to turn away most anti-tank rounds, but that same hardness made it prone to cracking under stress or rapid temperature changes, a fundamental trade-off in metallurgy. It was the kind of mistake that happened when production pressure overrode engineering discipline, when deadlines mattered more than proper procedure. "Run complete tests on every accessible surface," Patterson ordered, his voice carrying the weight of professional concern. "I want to know if this is localized or systemic, if we are looking at one bad batch or a fundamental flaw in their entire production process." Over the following days, a disturbing pattern emerged that confirmed Patterson's worst suspicions about German manufacturing capabilities. The Tiger's armor, while impressively thick and intimidating in appearance, showed inconsistent quality throughout every section they examined. Some sections tested with the hardness of the finest tool steel, meeting or exceeding any reasonable armor specification. Others were softer, more ductile and flexible, but still incredibly thick and potentially effective. The variation suggested that different portions of the hull came from different production runs, possibly even different factories, with no standardized quality control between them. The welds connecting armor plates showed particular weakness, with micro cracks visible around many joints, the kind of flaws that would propagate under thermal stress or impact shock. On the sixth day, a German prisoner was brought to the site under heavy guard, the jeep kicking up dust as it approached the repair area. Hauptmann Friedrich Weber had commanded the disabled Tiger before ordering his crew to abandon it when the track failure made it impossible to retreat with the withdrawing forces. Weber was 34 years old, a career soldier who had served in armored units since 1937, first with light tanks in training exercises, then with Panzer IIIs during the early campaigns, and finally with Tigers since their introduction in late 1942. He spoke adequate English, learned during a pre-conflict year, studying mechanical engineering at a university in Britain, a detail that made him valuable for technical interrogation. His uniform was dusty and worn, his face showing the exhaustion of men who had been fighting in North Africa for months without adequate supplies or reinforcement. Intelligence officers hoped he might provide insight into the tank's systems, maintenance requirements, tactical employment, anything that might give Allied forces an advantage in future encounters with these formidable machines. Weber's reaction to seeing Americans working on his tank was complex, a mixture of professional interest, national pride, and bitter resignation. He approached slowly, hands bound with rope rather than metal cuffs, flanked by 2 military police guards who kept their rifles ready but not quite pointed at him. For several long moments he simply stared at the Tiger, at the hull plates that had protected him through a dozen engagements, at the cannon that had defeated so many Allied vehicles. His expression was difficult to read, something between loss and relief. Then he began to laugh, a bitter sound without humor, the kind of laughter that comes when reality confirms your worst suspicions. "You think you have captured a treasure," Weber said in accented English, his voice carrying clearly in the desert air. "You think this tank is proof of our technological superiority. You have captured a beautiful catastrophe, a monument to what happens when engineers are asked to build perfection without the resources to sustain it." Hayes gestured for the guards to allow Weber closer, though they remained alert. The German officer's eyes moved over the tank with the familiarity of intimate knowledge. "What do you mean, Hauptmann?" Hayes asked. Weber pointed to the armor plating. "You see this metal, yes? This is our pride. 100 millimeters of face-hardened steel. Nothing you have can penetrate it from the front at normal combat range. Your Sherman guns, your tank destroyer guns, they bounce off like rain. But do you know what this armor costs us?" He did not wait for an answer. "Each Tiger needs special steel alloys, chrome, molybdenum, nickel. "We do not have these metals anymore, not enough. The strategic materials are gone, sent to the bottom of the Atlantic by your ships, or never delivered by mines that are blockaded. So our metallurgists, they must improvise. They increase carbon content to maintain hardness. They adjust the tempering process. They make the armor hard enough to stop your shells, but the metal becomes stressed, unpredictable." Chen had been listening intently. "That explains the inconsistency," he said. "You're working with whatever alloys you can source, adjusting the process constantly." Weber nodded. "Every batch is different. The factories do their best, but they are working with substitute materials. Reduced processing time, workers who are exhausted or inexperienced because the skilled men are at the front." He gestured toward the visible cracks. "These fractures, they appear after the tank experiences combat stress. The metal is too hard, too brittle. In winter, it becomes worse. Temperatures below zero can cause the armor to crack from thermal stress alone." Patterson found himself revising years of assumptions. The Americans had feared the Tiger since first reports emerged from the Eastern Front. Intelligence briefs described an impervious monster that could engage Allied armor from ranges where return fire was impossible. But standing here, seeing the metallurgical evidence, understanding the production compromises, the picture changed. The Tiger was not invincible, it was desperate. Hayes began asking technical questions, and Weber answered with the resignation of a man who understood the larger implications. The Tiger, Weber explained, required a Maybach engine producing 700 horsepower just to move its massive weight. The transmission was so complex that only a handful of factories could manufacture it. The interleaved road wheel system, designed to distribute weight and improve cross-country performance, constantly packed with mud and froze solid in winter conditions. Each Tiger needed 5 times the maintenance hours of a Sherman. "Your General Patton said something after the Sicily campaign." Weber observed quietly. "He said that quantity has a quality all its own. I did not understand this until I saw how you wage industrial warfare. You build acceptable tanks in overwhelming numbers. You replace losses faster than we can inflict them. You equip your tanks with radios, every single one, so they coordinate like a pack. We build masterpieces in tiny numbers, and each loss is irreplaceable." The work of repairing the Tiger continued for 3 weeks. Patterson's team discovered that the track failure resulted from a simple broken pin, a 5-minute repair under normal circumstances. But the interleaved wheels meant they had to remove half the suspension system to reach the damaged link. The job required 87 hours of labor. Mitchell, working deep in the engine compartment, made another discovery. "Sarge," he called out, "you're going to want to see this." Patterson crawled under the hull. Mitchell had removed an inspection plate from the transmission. Inside, instead of precision-machined gears, they found components that showed clear signs of rushed manufacturing. Tool marks were visible on gear teeth. Tolerances were inconsistent. Some parts appeared hand-finished rather than properly machined. "This is not factory-standard work," Chen observed, examining a gear. "This looks like field-expedient repair, except it's original equipment." Weber, who had become an unofficial consultant to the repair effort, explained, "By 1943, the factory workers are not the same men who built the first Tigers. The skilled workers are conscripted. We have women, old men, forced laborers who do not care about precision. The manufacturing standards we once maintained are no longer possible. Each tank that leaves the factory is a miracle of improvisation." The Tiger was finally restored to operational status on April 3rd, after 21 days of intensive work. Hayes insisted on a comprehensive test program before shipping the tank to Aberdeen Proving Ground for more detailed analysis. They spent 5 days running the tank through various terrain and scenarios, documenting performance, fuel consumption, and mechanical reliability with scientific rigor. Each test was photographed, measured, and recorded in duplicate. They drove it across soft sand, over rocky terrain, through simulated combat maneuvers. They measured acceleration, turning radius, main gun traverse speed, and a dozen other performance parameters. The results were illuminating and devastating to the myth of German technical superiority that had grown in the minds of Allied soldiers who faced these machines in combat. The Tiger consumed 600 liters of fuel per 100 kilometers of operation. a staggering amount compared to 250 liters for a Sherman covering the same distance. Patterson calculated that maintaining a Tiger company in sustained operations would require more than double the fuel logistics of an equivalent Sherman unit, straining supply lines that were already stretched across thousands of kilometers of ocean and desert. Its maximum speed of 45 kilometers per hour was indeed impressive given its massive weight, but the transmission overheated after sustained high-speed operation, the cooling system inadequate for the heat generated by pushing 56 tons at that pace. Twice during testing, they had to stop and wait for components to cool before continuing. The armor, while thick and intimidating, showed new stress cracks after the engine was run continuously for 6 hours, the thermal expansion and contraction revealing the brittleness Weber had described. The metal was literally cracking from the stress of simply operating the tank under normal conditions, without any combat damage or external impact. Patterson compiled a comprehensive report that would be distributed throughout Allied armored commands. His conclusions reshaped tactical thinking. The Tiger was indeed a formidable weapons system when properly maintained and deployed. But it was not the invincible superweapon that propaganda suggested. It was a product of industrial desperation, built with substitute materials by an exhausted workforce, maintained by overextended logistics, and fielded by an army that could not replace losses. One evening, as the testing phase concluded, Patterson and Weber sat on the Tiger's hull, sharing coffee that the American had brewed. The sunset painted the desert in shades of copper and gold. Two mechanics, separated by uniform and allegiance, united by understanding of machines. "You know what is strange?" Weber said quietly. "I commanded this tank for 9 months. I trusted my life to this armor. But I always knew in my heart that we were trying to achieve perfection while you were achieving adequacy at scale. Your Sherman is not better than my Tiger in a single engagement, but you will have 10 Shermans for every Tiger. And when my Tiger breaks down, I wait weeks for parts. When your Sherman breaks down, you abandon it and get a new one." Patterson nodded. "I spent 20 years building cars in Detroit," he said. "We learned that the perfect car nobody can afford is worthless. The good enough car that everyone can own changes the world. Same principle applies to tanks, I guess." Weber smiled sadly. "You understand something my commanders never accepted. This conflict will not be decided by the quality of individual weapons. It will be decided by production capacity, resource access, and the ability to sustain operations across vast distances. You have all these advantages. We have skill and desperation." The report Patterson submitted ran to 147 pages, including detailed photographs, metallurgical analyses, and tactical recommendations. The key findings revolutionized Allied understanding of German armored forces. The recommendation that had the most immediate impact was simple. Do not fear the Tiger. Respect it, understand its limitations, and exploit them. Allied tank crews were briefed on the Tiger's weaknesses. The side and rear armor was vulnerable. The complex transmission could be disabled by sustained fire at the drive sprocket. The tank was most dangerous at long range, but could be overwhelmed by coordinated attacks from multiple directions. Most importantly, crews learned that Tiger commanders were often hesitant to risk their irreplaceable tanks in uncertain situations, while Sherman commanders could take calculated risks knowing replacement was possible. Chen's metallurgical analysis traveled to research facilities in Britain and the United States. Scientists studied the stress patterns, the inconsistent hardness readings, the weld failures. They developed new armor-piercing rounds specifically designed to exploit the brittleness of over-hardened steel. The research contributed to improved American armor design, but more importantly, it revealed the extent of German industrial degradation. By late 1944, Allied intelligence had built a comprehensive picture of German tank production. The factories were bombed repeatedly. Essential alloy materials were increasingly unavailable. Skilled labor had been depleted. Production times increased while quality decreased. Each Tiger that rolled off the assembly line represented a triumph of will over resources, but it was a triumph that could not be sustained. Weber spent the remainder of the conflict in a prisoner of war camp in the United States. After the conflict ended, he wrote a memoir that included detailed descriptions of his experience with the captured Tiger. In it, he reflected on the moment he watched American mechanics repair his tank. "I understood then," he wrote, "that we had already lost. Not because they were better soldiers, but because they had better factories. They could afford to be good enough because they could be good enough in overwhelming quantity." Patterson returned to Detroit after the conflict. He brought with him notebooks filled with technical observations, photographs, and insights that would influence American automotive engineering for decades. The lessons learned from examining German over-engineering affected everything from production planning to quality control philosophy. The idea that perfection was the enemy of sufficiency became a guiding principle in American manufacturing. Mitchell used his GI Bill benefits to study mechanical engineering. He eventually worked for Chrysler, where he became an expert in armor metallurgy. He kept a photograph on his desk for 40 years, himself standing next to the Tiger in Tunisia, a young private from Iowa dwarfed by a machine that represented everything he thought was invincible. Chen completed his degree in metallurgical engineering and spent his career working for the Department of Defense, studying armor technology. He published numerous papers on metal fatigue, stress fractures, and the relationship between hardness and brittleness. He always credited those 3 weeks in the Tunisian desert as the foundation of his understanding. "You cannot appreciate the importance of consistent manufacturing," he often told students, "until you see what happens when it breaks down." Hayes rose to the rank of full colonel and oversaw technical intelligence operations throughout the European campaign. His detailed analyses of captured equipment provided Allied commanders with crucial insights into German industrial capacity. After the conflict, he testified before Congress about the importance of maintaining robust industrial infrastructure. The conflict, he stated, was won in the factories as much as on the battlefields. The captured Tiger itself had an interesting fate. After testing concluded, it was shipped to the Aberdeen Proving Ground in Maryland. There it was subjected to extensive firing tests, helping engineers understand exactly how different weapons interacted with various armor types. The tank still sits in a museum today, one of a handful of Tigers preserved in the United States, its armor bearing the scars of American shells, but also the invisible legacy of German industrial desperation. The broader lesson of the Tiger's cracking armor resonated far beyond military circles. Industrial planners recognized that technological superiority without production capacity was ultimately futile. The post-conflict era saw an emphasis on manufacturing infrastructure, supply chain resilience, and the ability to rapidly scale production. The Cold War arms race that followed was as much about industrial capacity as weapon performance. For the men who worked on that Tiger in Tunisia, the experience was transformative. They had approached it with a mixture of fear and respect, believing they were examining a technological marvel. They left understanding they had witnessed industrial desperation, dressed in impressive armor. The Tiger was indeed a masterpiece of engineering, but it was a masterpiece built under impossible constraints, using substitute materials, by exhausted workers for a cause that could not sustain such expenditure. Patterson often reflected on his conversations with Weber. The German officer's candid assessment of his own side's weaknesses revealed more than any intelligence briefing could have provided. Weber understood that the conflict was not about individual battles, but about systemic capacity. The side that could sustain operations, replace losses, and maintain production would prevail regardless of tactical brilliance or technological innovation. The metallurgical findings from the Tiger analysis influenced armor development for generations. Engineers learned that armor design required balancing multiple competing factors: hardness versus brittleness, thickness versus weight, protection versus mobility, and cost versus performance. The German approach of maximizing protection at any cost proved unsustainable. The American approach of balanced design at scale proved decisive. In the decades that followed, military historians would debate the Tiger's legacy. Some emphasized its tactical superiority, pointing to its impressive combat record. Others highlighted its strategic failure, noting how few were produced relative to their resource consumption. But the mechanics who actually worked on captured examples understood a nuanced truth. The Tiger was simultaneously impressive and flawed, a testament to engineering skill and industrial limitation, a weapon that proved both the importance of quality and the supremacy of quantity. The cracks in the Tiger's armor were more than metallurgical defects. They were visible evidence of an industrial base under impossible strain, of substitute materials replacing strategic alloys, of rushed production schedules overriding quality control, of skilled workers replaced by inexperienced laborers. Each hairline fracture told a story of resource scarcity. Each inconsistent hardness reading revealed production desperation. Each weld failure indicated manufacturing degradation. For Patterson and his team, understanding why German armor kept cracking required looking beyond the immediate technical causes. The cracks resulted from overhardened steel, yes, but why was the steel overhardened? Because essential alloying elements were unavailable. Why were they unavailable? Because supply lines were disrupted and resource access was constrained. Why were resources constrained? Because the industrial war was already lost, even as individual battles continued. The Tiger tank, in this light, became a metaphor for the entire German approach to the conflict. Technologically impressive, tactically effective in specific scenarios, but strategically untenable. It represented an attempt to achieve victory through individual superiority rather than systemic strength. The Americans, by contrast, embraced systemic strength even when individual components were merely adequate. This philosophical difference extended beyond tanks. German aircraft were often superior in performance, but required excessive maintenance and specialized parts. German small arms were beautifully machined, but expensive to produce. German uniforms were tailored and well-designed, but resource-intensive. In each case, the pursuit of excellence created vulnerabilities that the Allied emphasis on adequacy at scale could exploit. The mechanics who repaired that Tiger learned a lesson that would echo through military planning for the next 80 years. Wars are won by logistics, industrial capacity, and sustainable systems, not by individual technological marvels. A perfect weapon you cannot maintain, cannot replace, and cannot afford to risk is ultimately less valuable than a good weapon you can field in overwhelming numbers. As the years passed and the immediate memory of the conflict faded, the Tiger acquired mythical status. It appeared in films, books, and documentaries as the ultimate tank, the fearsome predator that Allied forces struggled to defeat. This mythologization obscured the reality that Patterson and his team had documented in Tunisia. The Tiger was fearsome, yes, but it was also fragile, resource-intensive, and ultimately representative of an approach to warfare that could not succeed. The men who actually touched the Tiger's cracking armor, who measured its inconsistent hardness, who documented its production flaws, they understood a more complete truth. They had not just repaired a tank, they had performed an autopsy on a dying industrial system. Every crack in the armor was a symptom of industrial illness. Every substitute material was evidence of resource starvation. Every rushed weld was proof of unsustainable production pressure. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.